Hi, my name is Raswanth Srinivasan, and this is Lab 4 Oscillations for Physics 2211. So, for the introduction, the main goal of this lab is to analyze the motion of a mass, which is attached to a spring while it moves in an arc, and compare predicted motion with observed motion. The data of the energy changes for predicted motion will be plotted using GlowScript and observed to see if the model follows the energy principle. A recap of the results are that the change in the system's total energy is zero, and this conclusion can be reached by analyzing all of the other energies in the system. Patterns in predicted motion and observed motion are also similar. So for the introduction of the fundamental principles, Newton's second law plays a big part. Newton's second law of motion states that the change in momentum of an object is related to the change in time and net force applied on the object. And the formulas are shown right there, where F net is equal to the change in momentum over the change in time. The velocity update formula is also used for this lab, and it is implemented in the GlowScript code, and it is shown right below. The position update formula is also useful and utilizing GlowScript, and it can be derived from the velocity update formula. So some more fundamental principles. The energy principle is big, also known as the principle of conservation of energy. It states that the energy cannot be created or destroyed in an isolated system. It can only change forms. In other words, the total energy within a closed system remains constant over time, with transformations occurring between different forms of energy, such as kinetic, potential, and thermal energy. And a formula is shown below. It is essential for the system to be defined when identifying the types of energy which are in the scenario and how the surroundings are at play with this. In this case, the system is the earth, spring, and mass, and the surrounding is nothing. We set the surrounding to nothing and include all elements that do work on the object in the system so that the change in energy in the system can be set to zero. So here's the tracker analysis for the observed motion. We have the graphs of both the x and y positions, and then the object's mass is 0.402 kilograms. The value of L hat is 0.7 meters. The start time is 0, end time is 6.648 seconds. Delta T is 0.095, which was created using the PHYS, and then the initial position and initial velocity are shown below. So the initial conditions for computational model and constants are shown below. All of these were used in the GlowScript code, and the formula for the oscillation period is shown to the left, as well as the forces that contribute to the net force. So some more related equations for the computational model are shown below. So here we derive the value of L and S, and then we also work with all the different energies that are in the system. So for the iteration for the computational model, the code is shown here, and the energies involved are delta E equals delta US plus delta K plus delta UG, which is all equal to 0. And some additional equations which were involved were the force of gravity, the spring force, and the value of S. So the results are shown here, and they're shown through three different graphs: the Y position versus time, X position versus time, and change in energy versus time. Some possible errors was that the tracker is not accurately representing the experimental model due to accurately placing the center of mass tracker. All work from surroundings also may not be accounted for. So what does it mean? Is the energy principle satisfied? Yes. There are multiple ways to observe that the energy principle is satisfied. First off, it can be seen that the change in total energy, which is the yellow line, is 0 throughout the entire time. Additionally, adding together the changes in kinetic energy, spring potential energy, and gravitational potential energy gives a sum of 0. This happens because the kinetic energy and spring potential energy sums to the gravitational potential energy, which is in the opposite direction. So expanding upon the what does it mean, deriving oscillation periods by using the position from tracker. So these were calculated by finding the average time between three trophs. The average oscillation period for the X position was 1.609 seconds, and the average oscillation period for the Y position was 1.789 seconds. The difference between the oscillations for the different axes of 0.18 seconds can create discrepancies in the spring force, spring constant, and spring potential energy. And that's the end. Thank you for watching.